uh, our new section about the galaxies and the cosmology section, right? So that will be the next one. So before we start that, let me quickly finish this part that I have started talking. Remember that we talk about the proper motions of a star and what is space velocity and these kind of stuff, right? That is about the motion of stars. And apart from that, uh, let me explain to you that there is another motion that we can talk about stars. That is the rotation of a star, right? Probably you have not heard about it before, but uh, we can uh, we can talk about the movements of the stars. So if I remind what we have discussed last time is the movements of the stars along the line of sight. So that means the radial velocity. And then we have also discussed about the movements across the sky, right? So that is called proper motion of a star, right? So those are the two things that we talked and we discussed how to measure the proper motion and how to measure the radial velocity, and then how to combine those at the end to find the space velocity, right? So that is what we have discussed uh, last time. And apart from that, we can also talk about the rotations of a star, right? Now, what stars actually rotates its own axis. What I am focusing here is how to measure these rotations, right? Now, all you know about the Doppler effect, right? So this Doppler effect can be used to measure how fast the particular star rotates, right? So you have probably heard about the Doppler effect, that you can use it to measure how fast a particular star is moving away from you, move towards to you, right? So that's what you have probably heard about the Doppler effect. Now in astronomy, we are using Doppler effect for different places. Here we use Doppler effect to get an idea about the rotation speed of a star, right? So what actually happened is, due to the Doppler effect, uh, the lines that you have in the spectrum. So when we say that one side, when you think about rotation of a star, one side of the star will come towards to you and the other side will move away from you, right? So that's what actually happens. Now, because of that, the side that rotates towards to you will be shifted to shorter wavelengths, and the lines in the opposite edge, which means that they are shifting away from you, those lines will be shifted to longer wavelengths, right? Now, if a particular star is rotating very rapidly, there will be a great spread of these two Doppler shifts, right? Because one is quickly approaching, one side is quickly approaching to you, and the other side is moving faster away from you. So that will make a greater spread of this Doppler shift, right? Now, what that means is actually these spectral lines will be quite broad, right? So we have a specific name in astronomy for that, and this is called line broadening, right? So you may probably hearing this word for the first time, so make sure that you remember that word. So this is called line broadening. So basically, this line broadening can tell you the speed at which the star rotates. Now, if I show it to you from an example, here is a star. Basically, it is actually not rotating, right? So then you will have a line right here with a little dip like this. However, if the star is rotating, you can see that this side of the star is coming towards to you, which means that will be blue shifted, and the other side of the star will be moving away from us. So that side will be red shifted. As a result of that, this line is a little bit broader compared to this one. That is what we call as a line broadening, right? Now, if you compare the two graphs here, the dip is like this for the first one. Once it gets a little bit broader, you will get uh, higher with this absorption line, right? So right here. So that is what we called as line broadening, right? So basically you will have broader spectra lines for a rotating star compared to a non-rotating star, right? That is another application in physics, specifically in Doppler shift that we use in astronomy. And here is a comparison of two rotation speeds for two stars, Altair and our own sun. Our own sun actually take around, the rotation period is around 24 to 30 days, while the star in the left-hand side, which we called as the star Altair, has a rotation period of 6.5 hours, right? Right, so that's about the rotational motion of a star. And then we will move on to talk about the binary star systems, right? So basically, when we talk about the stellar evolution and everything, what we have discussed is what actually happens to a single star, right? And also different stages of the life, I mean, different stages of its life, right? And basically we talk about the fusion reactions that happens inside the star, and then how star evolves into different phases such as red giants and then the white dwarfs. And if the star is a high mass star, then it will become a neutron star and then a black hole, like that, right? Now what I am talking here is a different section. This is about binary star systems. And the binary stars are actually one of the very important observations that we have for due to different reasons. And the basically the binary star systems means that you have always two stars, right? So those type of stars systems we called as binary star systems. Actually, most of the stars that we see are parts of these multiple star systems revolving around the common center of mass. Most of the time, what we see as are actually binary stars, right? So we see multiple stars that they are revolving around the common center of mass. So if you have, let's say, two stars, there should be a center of mass that is common to both of those stars, right? So what normally happens is they will rotate around that center of mass, right? Now, if there are two star systems, then we call that as a binary star system. So what that means is there may be star systems that can have stars more than two. Maybe there may be three stars, four stars involved in some of these star systems, right? But in this course, what we are focusing on only about this binary star systems. Now, there are different types of binary systems that we used to define in astronomy based on how we identify those, right? Now, one of those types is called visual binaries. Visual binaries means they are very close to Earth, so that you can clearly see that there are two stars individually from a telescope. So that means you use a telescope and look at this star system, and you can clearly see that there are two stars separately, right? So those type of binary star systems are called as visual binaries, right? And there are other type of binaries. The second type is called astrometric binaries. So what that means is there are two stars in the system, but you cannot observe both stars separately, or you cannot resolve those two stars by using a telescope, right? Now, these type of stars are actually, you cannot, sometimes you can detect one star, but the other one you cannot observe, right? Now, these type of stars can be detected using gravitational influence of the primary star, right? So this method is usually called as astrometric binaries. So this is very useful when you have, binary systems that are too far away. Those stars are that are too close to one star. right? So that means if the two stars are very close together, it is hard to resolve it from a telescope. Or if they are so far away, then also it is hard to, uh, observe. There are two stars, right? Then, so these kind of star systems, then you have to use this astrometric system, right? You can even calculate the mass of a binary star system using this particular equation that you see here. If the system's mass is like, let's say, m1 plus m2, then the total mass of the system, it should be equal to r to the power 3 over p squared, right? So this is basically the Kepler's law that we have discussed before. P and R are between the stars can be obtained the sum of the masses of two stars. So you can basically find the sum of the two stars, mass of the two stars. If you can use another method to, let's say, measure the mass of the primary star, then using this equation, you can actually find the mass of the secondary star, right? So that is called astrometric binaries. And then there is the third type of binary star system. This is called spectroscopic binaries. And you can see that this name itself suggests the method that we are using to detect these kind of star systems. The spectroscopic binary means that when you look at those stars, it appears that there is a single star. When you take a photograph or take a visual observation from a telescope, but when you look at the spectroscopy, so that means if you look at the spectroscope, then it will show up as a double star, or there are two stars. So these type of star systems are called spectroscopic binaries. Now here is an example that if you have two stars, you can see that if they move, one moving away from us, the other one moving towards you, then you will have two spectral lines like that. However, if the orientation is such that the two stars moving perpendicular to us, that means the star is B is moving to this direction and the star A is moving into this direction, and you are observing from here, both are neither come towards or away from you. So that means you will not see any change in the spectrum, right? So you just see this kind of one line, and then again, when the opposite thing happens, when A is moving away and B is coming towards you, then again you will have two lines. However, now the B and A are shifted their directions, right? So B is now here and A is now here, like that. So in this way, you can detect spectroscopic binaries, right? And also you can actually find the radial velocities of spectroscopic binaries. You can see that these are the two stars, and you can plot the radial velocities in the time. You can see the star when it is in this orientation, number one, you know that A is coming towards you and B is moving away from us. So that means the velocity of A should be towards you, and the B is moving away from you. And then number three is the opposite, directly opposite. So that's what you can see from this graph, right? So I guess you can understand it. And the fourth type of binary star system is called eclipsing binaries. So what happens here is there are two stars. So they are oriented in such a way that one star can pass the other star, right? So because of that, they are called eclipsing binaries. So what that means is one star will go around the other one. Because of that, at certain points, one star may cover the central star partially or completely. So we call these type of events as eclipse, right? Because it kind of, covers the other star at the central region. So here is an example for that. And you can see that there are two stars in the diagram. The one in this pink color is at the center, which is a larger, let's say a red type star, and there is a smaller star that goes around it, the size of the star is smaller. So that means the area of the star is smaller. However, it's so you can see the light curve that that is relevant to this particular binary system. The light curve means in astronomy is basically how the brightness change over the time. You can see that this axis is the time and this axis is the brightness, right? So what happens is there is this the star that goes around this large star. You can see that at point 1, right here, the number 1 is relevant to this position right here. At that position, what has happened is when you look from your side, you can see the brightness coming from both stars separately, because none of them is covered by the other one, right? At point 1, you can see you have the light from this star coming towards you, and this is plus this star, the light coming from that as well. So you can add together those two, so that you will get the maximum amount of brightness. So that's what this number 1 means in the curve. And when you go to the number 2 position, you can see that the blue star is completely covered by this large red star, right? And then you can see there is the smaller star is completely covered. So which means when you look at this particular system from your side, what you will observe is only this large star, right? The brightness from that smaller star is completely covered. So that is why the brightness is completely dropped here up to the point 2, right? And then again, when it comes to the 3rd position, you can again see both stars from your side, the light from this star plus light from this red star. So which means once again, it will come to the maximum brightness, like in this position. And then when the blue star comes in front of this large red star, you can see that the blue star covers only a small portion from the red star. And because of that, you will get the complete brightness from the blue star, and a small part of the red star will be covered. So then there is a drop in the brightness, right? So there is a small drop like that. There is a special thing that you need to understand: the drop of the brightness when you at number 2 position, where you have this blue star is completely behind the red one, is larger compared to the other orientation where you have the blue star in front of the red one, right? So you need to think about why this happens, right? Actually, is there anyone who can explain it? Why this drop is larger compared to this one right here? Anybody likes to give an answer for that? No answer. Actually, what happens here is you can see this blue star represent that it's a very hot star, right? So the temperature of that particular star is larger compared to this large red star. That's why it is represented from the blue color. And because of that, you know that the luminosity or the brightness of a star depends on 2 parameters. We have discussed that before. Those 2 parameters are: number 1, temperature; number 2, the surface area, right? So those 2 are the parameters that the brightness depends on, right? And because of that, you know that the effect of the temperature is greater compared to the effect of the surface area. If you remember this Boltzmann, the luminosity equation, that is actually A T to the power 4, right? So there is a fourth power for the temperature, and because of that, even though the smaller star, the surface area of the smaller star is not that much, when it is completely covered by the large star, the brightness coming from the smaller star is completely covered. However, the brightness is larger for that smaller star because it has a higher temperature, right, compared to the larger one. So that's why this dip is larger compared to this particular position, right? And finally, so those are the four types of binary star systems. And finally, before I move on to the next system, let me just give you one important relation about the stars that we could not talk before. This is called mass luminosity relation. So this is a very nice relation to get an idea about the mass of a particular star, right? You can see that uh, most of the stars from this graph, there is a relation between the mass and the luminosity of a star, right? And this relation is given here in the left-hand side. Luminosity is approximately equal to the 3.9 power of the mass, or you can get, you can assume it also as the fourth power of the mass, right? So what this means is, if I take an example, if you have a star, if you have two stars that you have a mass difference by a factor of 2, then the massive star will be 16 times brighter. That is 2 to the power 4. You have like power 3.9 here, so I approximate it as a power of 4, right? So make sure that you have this relationship uh, that you remember, right? So this is one of the important relationships in astronomy. And also, even if you can't remember this one, just as an approximation, remember this one at least, right? You can take that approximation m to the power 4 always. So there is nothing wrong with that, right? You just take 3.9 as 4. So that's okay. Right, so that is the end of that section about the stars. Anybody have any questions up to here before we move on to the next section, which is like a completely new section about the galaxies? By the way, I was actually thinking about doing you a little more about the general relativity, about this, Schwarzschild radius and Schwarzschild metric, those kind of stuff. But seems like you are, according to your syllabus, it may be too much for you to go into more detail about the general relativity, because whatever you have learned up to now should be enough for you for that section. So I will be moving to the next section about the galaxies now. Before we move on to that, in between, while I am pulling up this presentation, if any of you have any questions, feel free to ask, right? By the way, most probably you will have your second ICE exam in the next week, right? So I'm going to send you a paper by the end of this week. So you will have it scheduled by the department as you did last time, right, at some point. Right. Can one of you confirm me whether you can see my screen right now about the galaxies? Please. Right. Thank you. Uh, Right. So far, we have been talking about the planets, moon, sun, and the stars, and those kind of stuff. Right. So now we are moving to a completely the next scale uh, in that we need to talk about in this course, which is about the galaxies. Right. Now, with the galaxies, there are a lot of things are related here about the expansion of the universe, dark matter, dark energy, those kind of lot of things are involved. This is called like now we are basically going to the large scale structure of the universe rather than looking at the stars and all of these, stars and planets in our Milky Way and surrounding galaxies. Right? We are moving on to the bigger scale to talk about the galaxies, and this is where all these dark matter, dark energy, expansion of the universe, and those kind of things comes into play, right? And we will see how these things, how we can relate those things to these lessons later. Now, when we talk about the galaxies, the first thing that comes to your mind is the Milky Way, which is our own galaxy, right? Now, we have encountered many different types of stars that we discussed, and we saw that how these stars evolve and those kind of things. Now we are moving on to the topic about the galaxies, and what we have known for a long time is the night sky that we are looking at is full of stars, right? So this is what we used to know. However, it is only recent times that we learn that there are different galaxies within our universe, right? Uh, and we will begin the discovery of other galaxies. Now, there are actually questions asking which chapters that your second IELTS paper will be. I think I have answered this several times in previous lectures, which I can see that some of you may be not listening to that. Right? So just go back, and I'm going to upload those lectures to the recorded lectures. Just go and look at the lectures, and you will see which I have explained, like which chapters that we will be have to look at. That's basically will be based on the stars, right? The things that we talk about, the stars will be primarily there, which is up to last the one that I just finished will also involve, but things about the galaxies will not appear there, right? Right. So we will actually very recently we knew that there are other galaxies rather than our own Milky Way. So we will begin with a story about the discovery of other galaxies, because this story is very interesting, and you will get while understanding this story about the galaxies and their properties, you will also understand that how people approach for these discoveries, which is for me that is also important, right? And we will learn about the structure of the Milky Way and how stars, interstellar matter, and even something called unseen dark matter are spread throughout our galaxy, right? First, we will look at the story of this discovery of galaxies, and then we will move on to look at how the stars, interstellar matter, and those kind of stuff are spread inside our galaxy, right? So we have learned about interstellar matter, stars, planets, those kind of stuff previously. Now we are going to look at how they are spread out in our galaxy, right? Right. Now, in very past, I mean, before let's say around in the past century, people did not know that there are, an object or a entity called galaxy, right? So they use this word called nebula. Nebula means normally a collection of like, a gas cloud kind of thing. So observations of the night sky give us the impression that stars and the nebula may all associated with one another, right? So this shows the idea that initially we had. There are stars there are nebulas. The name nebula is actually what they refer as the galaxies now. But at the ancient time, they did not know that there are galaxies. So they use this nebula, which is like small island kind of, collection of stars, those kind of things. Now, if you look at the Milky Way band in the sky, it seems that it indicates a pattern of grouping of stars in the sky. So if you look at the Milky Way, you will see that there are groups of stars in here and there, right? Which is apparent to even for the naked eye. If you go to like a dark area in the sky and look at this Milky Way band, you will identify that there are groups of stars at different places on this Milky Way band, right? And when Galileo invented this telescope, he looked at the Milky Way with the telescope and they found that there are many more faint stars there in the Milky Way. And so earlier on, what the people had this idea about what people knew was that the Milky Way group, so they called that as a Milky Way group at that time, was the universe itself. So that was the idea. The Milky Way is the only thing that you can see as a group that should be the universe, right? So there is nothing else there. So that was the idea that had for these ancient astronomers. However, in early 1700, there was a speculation that there may be many more stars beyond the confines of the Milky Way itself, right? So there was this idea came in 1700 that there may be more stars that are beyond our Milky Way. Right? Initially, what they thought was Milky Way is the universe, everything is inside it. And later, this speculation comes that all these, there may be some other stars that are beyond our Milky Way, right? And there are two astronomers or two observers basically involved in this idea in two different ways. There was an astronomer called Immanuel Kant who was the first proposed this theory that there may be more stars beyond our Milky Way, and observations with better telescopes identified spiral nebula which were thought to be possible collection of distant stars. Now, when they had this telescope, they observed the sky and they show a spiral nebula, right? So they call this as a nebula because they didn't have a proper name at that time. Nebula which were thought to be possible collection of distant stars that were comparable to the Milky Way. So they thought that this spiral nebula that they saw from a telescope, now you should have a curiosity in your mind what they have seen at this time, right? So they observe from the telescope, they show a collection of another set of collection of stars that are far away. So this Immanuel Kant, he had this idea about this collection of stars that they referred as a spiral nebula. So they probably have seen the spiral structure as well. Maybe some distant stars, which are more or less like our Milky Way, right? So that was his idea. And in 1920, there was this famous debate took place between two well-known astronomers called Shapley and Hertz. So in 1700, so they have these observations, but they didn't know, right, what was that. And then there were two astronomers, Harold Shapley and Hertz. So they argued, the Shapley argued that these nebulas were in our galaxy. So what they have seen here from the telescope, as I explained here, is spiral nebula. So Shapley argued that these nebulas were in our galaxy. So he thought that this is in our galaxy. There is no other nebula or galaxies outside there. So that was his argument. But the other astronomer K.V.S. argued that these nebula were very distant, not in our Milky Way. Right? So they did not know. And there was no way of identifying this. The problem was that at that time there is no method to measure their distances. Now you can see the idea here, right? Now if they are inside the Milky Way, to decide whether this nebula, spiral nebula that they have observed, they need to decide whether this is inside the Milky Way, or this is in a different place in the universe. So that was the problem. And two people are arguing that. One is arguing this nebula were in our galaxy, and the other one is telling this is a very distant one, not in our Milky Way. Now, the problem is that how to resolve this issue now. The major challenge was that you can see that even for you, if you need to resolve this issue, then you need to measure the distance to this nebula, right? Once you measure the distance, if you see that this distance is within the Milky Way range, then you can decide, okay, this nebula is also a part of the Milky Way. Or if it is so far away, then you can decide, okay, this is outside the Milky Way. So that is the basic idea. But the problem is that at that time, there was no way to measure their distances. So then astronomers were trying to find a method to find distances. Now, if you remember, we talked about a method to find distances in our Milky Way for our stars. So that was called parallax method. And if you remember, the equation was like distance equal to 1 over parallax. And this parallax has to measure in terms of arc seconds. Then you will get the distance in terms of parsecs, right? So that was what we have discussed. But this parallax method only works for a certain distances. So the stars, the close by the stars for us, it's okay. We can use that parallax method. But in they are so far away, it is hard to get accurate distances. Because you will have a very small parallax, then you cannot measure it. Now, because of that, astronomers now have to think about at that time to a method that you can measure the distances to these nebula so that they can resolve this problem. Right. Now, thankfully, so they came up with a new method of measuring distances. Now, this is what is, you can see that how astronomers and scientists, they overcome these challenges, right? So this discovery of new method of measuring distances is what helped to resolve this issue, right? Now, this new method involves a certain type of stars called Cepheid stars, right? There is a specific name. Now you can see that the Cepheid stars, they have used this type of Cepheid stars to measure the distances, right? Now you may be wondering what are these Cepheid stars now, right? So it's a completely new one for you. Cepheid stars actually a certain type of stars. They regularly vary their brightness, and as they pulsate, and their periods of variation is range from 1 to 50 days, right? So you can see that these are stars, but they have a special property. So they change their brightness, right? And this change in brightness had certain periods. Some of them change their brightness within 1 day, and some of them even can go up to 50 days. So these stars are called Cepheid stars, right? And in 1908, there was a lady astronomer called Henrietta Levy who measured the period of the Cepheid stars and the luminosity of a large number of Cepheid stars. So she did the survey now. She tried to detect all these Cepheid stars and then measured the period of the star and the luminosity of the star. Right? She did this for a large number of stars. Now, to measure the luminosity, she also had to estimate the distance to these stars. Right? The luminosity means measuring the absolute magnitude. You know that to measure the absolute magnitude, you need to know the distance to those stars. Now, she had an amazing discovery, right? So it is that she discovered that there is a relationship between the period of a Cepheid, a star, or we used to tell a Cepheid, and its average luminosity. And we gave a special name for this one. This is called period luminosity relationship. And this is one of the very important relationships that you will come across when you learn astronomy. Because this is very important to measure the distances, right? So what she found was that the most luminous Cepheid stars have longest periods, while less luminous or less brighter stars had shorter periods. And here is her finding that is nicely shown up in this graph. This axis is period of those Cepheid stars, and this axis is the average luminosity. So she discovered this relationship, or found this relationship. You can see that when you plot the period of a certain star and its luminosity, they all fall in this linear relationship. So you can fit a line for that, right? And here is the sample light curve of a Cepheid star. And light curve means, once again, how the brightness, now here it is depicted from the magnitude, brightness change over the time. So that is what we called as the light curve, right? Now you can see that from this graph, once you know this relationship, if you find a Cepheid star at a certain location, right? So let's say now the problem we had was how to measure the distance to this nebula. Now, if you can find few, let's say one Cepheid star means the star that changes its brightness regularly. You can find that kind of a star, then you can observe or measure the period of that, how many days it will take for it to reduce the brightness and come into the same brightness again, right? So if you know that, then let's say it's 10 days, you can go to this graph and look at, okay, this particular Cepheid time that nebula has a period of 10 days. And what you can do is, you can use this graph. If this is 10 days, the relevant average luminosity of that particular star should be whatever this value right here. Then you can take that value and plug it here in this equation, right? So this equation can be derived easily. So I'm just giving you the equation here, make it simple. So this is the luminosity that we are going to get from the graph. And this is the luminosity of our sun, which is a standard value. And those can be related into the absolute magnitude of a star, right? So if you know the absolute magnitude, so you can basically, if you know the luminosity from this relationship, you can find the absolute magnitude, right? And once it is done, if you know the absolute magnitude of a star, apparent magnitude you can measure, because apparent magnitude is the brightness as you see it without considering this the distance, right? Because of that, you can easily find the apparent brightness. Once you know the absolute brightness, absolute magnitude, and the apparent magnitude, you can easily find the distance, right? So that's what they did. Right? So from this graph, you can, these 4 pictures, I am trying to show you what actually you have to do. First step, you go outside and look at whatever the particular nebula and try to find the star, which is a Cepheid star. Then you try to find the period of that. Once you find the period, you can go into this picture and use the period luminosity relationship to find the luminosity of that particular star. So once you find the luminosity, then you can again find the apparent brightness of the star as well, which is easy. Once you do the apparent brightness of the star, you know the apparent brightness. From this one, you can find the absolute magnitude. And once you know the apparent magnitude, you can use this equation right here. This is a rearrangement of the same equation that we use when we talk about the properties of the stars. So remember, we tried to find the magnitude of the stars now. So you are basically using the same equation. The only thing here is now you have a method to find the absolute magnitude for these Cepheid stars. Now you know the capital M value and you know the simple M value, which is the apparent magnitudes. You plug those values to this equation to find the distance. So that's how you find the distance, right? So I'm trying to incorporate this method now. So I'm just telling you a story how astronomers found a method to find the distances to these objects that are so far away. The close by objects, you can use the parallax method, right? Now, from this method, they were able to measure the distance to this Andromeda nebula. At that time, they were used to refer it as nebula. Now, I have explained what I have told you before here in this slide. I guess you can understand it. So basically, at the end, you are going to use this equation, right? M minus M equal phi log D over 10 to get the distance. Basically, what you see in this picture is you just take the inverse and rearrange the equation to find the distance. It is the same equation right here, right? So I have explained it here as well for you to understand. And now you know a method to find the distance. Now there should be a one to take this challenge and check who is correct, right? So Edwin Hubble took this challenge to resolve this debate whether this nebula that they are, looking at. Basically, I would like to tell the name now. This is Andromeda Nebula. That's how they call it here. Whether to think about this nebula belongs to our own galaxy or whether it's a different one, right? So what Edwin Hubble did was he used his newly built 100-inch telescope. Now you can see that we talked about the telescope as well. Now when it comes to this time, like 1920s, the technology of the telescopes has developed. So they were able to make one of these large telescopes, 2.5-meter telescope, which is still in Mount Wilson in Southern California. And this was actually the world's largest telescope at that time. Not anymore now, but it was the largest one in 1920. So what Hubble did was, from his telescopes, he photographed the Andromeda Nebula, and he was able to detect several Cepheid stars within it. And he used these Cepheid stars and measured the periods of those stars, then used that period luminosity relationship to find the distance to this nebula, and his result was this one right here. This nebula is around 1 million light years away, and modern distance estimates actually show that this is even further away, but this was what he found at that time, right? Now what is the conclusion now? We know the size of the Milky Way is smaller than this value 1. It's not 1 million light years, means it's go beyond the Milky Way very, very clearly, right? So because of that, at the end of this debate, it was found that this astronomer was correct. So that means the Andromeda is a different entity. So this is actually how astronomers found the Andromeda galaxy, and it was the first galaxy to discover, right? Now that was the story of finding the first galaxy, but now we know that the universe contains billions of galaxies, which are the Milky Way is just one of those, right? Each galaxy, now there are billions of galaxies, each galaxy contains billions of stars inside that for each galaxy. And apart from that, galaxies also contains interstellar matter and dark matter. Now, interstellar matter we talked previously. The dark matter, this is the first time that you are seeing this term. You have probably heard about this. So we will talk a little bit more about the dark matter in coming slides. Now, basically, these galaxies are held together by mutual gravitational attraction of its stars and other matter, right? Basically, galaxies are held together because you have interstellar matter, dark matter, and star. All these things are held together into a single entity, what we call as the galaxy, from the gravitational attraction, right? And that is for one galaxy. Usually these galaxies are usually separate from each other by vast regions, mostly empty space, right? So between galaxies, there are a lot of empty space. So because of that, galaxies are also called as island universes. Right. Now, just give me a minute here. Anybody have any questions up to here? Right. So it seems like you do not have any questions. Quite surprised, right? And so now keep that in mind. So let's come back to our own Milky Way and discuss a little bit about what kind of components that we have in the Milky Way. Right. Some of the properties. In 1785, one of the English astronomer called William Herschel, he constructed the first 3D map of the Milky Way. Now, to construct the map of the Milky Way, he needed to find the distances of the stars again, right? So he assumed that all the stars are at the same intrinsic brightness. So he assumed it in that way. And measuring the apparent magnitudes of the stars, he was able to make a rough estimate of the distance and then made a three-dimensional map of the Milky Way. Now here is his map. It's quite weird, right? So it's not what we know up to now. And this little mark right here is his assumption is that our solar system, which is close to the center of the galaxy. But now we know that it is not the case. Our solar system is not at the center of the galaxy. Actually, we are located on one of these spiral arms of the galaxy, and we are not at the center. Now, actually the problem that he had was the Herschel found that the Milky Way has a flattened disc-like shape. In addition, he also concluded that the sun lies at or near the center. Right? So he thought that the sun is at the center and Milky Way is a flattened disc-like shape. Now, this later assumption that the sun lies at the center of the Milky Way, we know that it is wrong now. And also Herschel's method had several shortcomings. So that means he did not realize this factor called extinction. I can't remember whether we discussed about this before. Actually, when you look at the sky, this light coming to you sometimes has to go through this interstellar matter, which is basically gas and dust. And you know what happened to light when it has to go through the gas and dust. What will happen is it will dim the starlight, so it will reduce the brightness, right? So basically, as a result of that, these distant stars will be more obscured than nearby stars because it has to go through. They have to go through a lot of, large amount of interstellar matter, which is basically gas and dust. Now, most of these distant stars may be invisible due to that reason, right? Maybe all the light may have been absorbed by the interstellar matter, right? So when Herschel made his map, he did not account this factor. So that means the one tends to see the same number of stars in any direction because you don't see the stars that are far away, right? Now this is why Herschel thought that maybe sun appeared to be at the center because when you look at, you see the same number of stars around, right? So that's a normal, understanding even we would have, right? If we did not know the technology and all the details, now you know. If you go outside and you see same number of stars everywhere, you may be thinking, okay, we are at the center, right? That's the idea. Right. Now, in order to make a more realistic map of the Milky Way, we have to have an improved technique to estimate the distances because Herschel thought that all the stars are at the same distance, which is not correct. Now, to have an improved technique to measure the distances, there is a different type of stars that now we are going to use. this set of stars are called RR Lyrae stars, which is again, they have the same property as the Cepheid stars. That means RR Lyrae also regularly change their brightness. So they are pulsating horizontal branch stars. Now, if they are in the similar kind of stars, why do you have two different names? The previous one we called as Cepheid stars. Now we have RR Lyrae, right? The reason is actually the main difference is that these stars, their period of variations are typically half a day to a day in length. So you can see that all these RR Lyrae stars roughly have the same period, and their period is very small. And because of that, they are kind of a little bit different than the Cepheid variables in that sense, right? And I will show in the next slide with the graph about this difference. And RR Lyrae have approximately the same average intrinsic brightness. So that is also another thing. So they basically have kind of same intrinsic brightness, and you will see it in the next graph. Basically, they are about 100 times more luminous than the sun, and their fixed absolute magnitude make them ideal for estimating the distance. So, once the all the RR Lyrae stars have the same absolute magnitude according to this period luminosity relationship, then it will be much easier for us to estimate the distance, right? You have one absolute magnitude for all the stars, and you just observe the apparent magnitude and then convert it to the distances, right? Now, these are the things. Now, some of you are asking what kind of things that I will be asking, for the exams and those things. Now, if I give you, like, let's say, information about the RR Lyrae stars and asking you to giving the apparent magnitudes of, let's say, 3 RR Lyrae stars, then I ask you to find the distance to these RR Lyrae stars. Maybe I will give you one magnitude, one absolute magnitude and 3 apparent magnitudes. Then you should have the knowledge from the astronomy to understand that if they are RR Lyrae stars, maybe they will have the same absolute magnitude for all 3 stars, right? Those kind of things, right? So make sure that you understand that basic idea, right? What is the difference? Why you study RR Lyrae stars separately? Why it has? What is the main difference between like RR Lyrae and Cepheid variables? Those kind of things are very important, right? Right. Now, from this particular graph, you can clearly see that there are 2 different clusters. These are Cepheid variables. And here is the RR Lyrae stars right here. You can see that all of them are, clusters around the same location, around 100 times. It's a little bit below that. We used to tell that it's 100 times more luminosity is 100 times the sun's luminosity. And their period is kind of varying in this region between 0.3 to 1 days. But they have kind of, similar kind of luminosities, right? Now it is this property that we have used to make a good map of the Milky Way, because this gives you accurate distances to different stars, right? You need to clearly understand it. These are Cepheid variables that we use to find the Andromeda galaxy and establish the idea that there are different galaxies in the universe. It is the RR Lyrae stars that we have used to make very accurate map of a Milky Way, because it's a good method of estimating the distances to these stars that are far away, right? But you sometimes cannot use the same method to find the other galaxies, right? So it's based on the Cepheid variables. Right, so then normally there are other properties of these RR Lyrae stars. RR Lyrae are specifically found mostly inside globular clusters. Now, I assume that all of you know what the globular cluster means. It's a type of star cluster that we had a separate chapter about star clusters. So go back and look at that if you can't remember it. So in 1970s, actually, the Harrow sharply identified that there are 93 globular clusters in our Milky Way. And then this allowed him to measure the distances to these clusters. And he found that these clusters are distributed in roughly spherical manner, and that's the nature of the globular cluster, as you know. And his estimate was the Milky Way is around 100,000 times light year in diameter. And he also found that sun was not at the center. And his estimate was that the sun is around 25,000 light years from the center of the Milky Way. So he found a lot of things from this information. And here is his map, right? So it's kind of more realistic compared to the other one. Right, now let's look at current understanding about the Milky Way and what is the structure of the Milky Way, right? Now we know that our galaxy, which is the Milky Way, has three distinct components. So that means there are three components that you can clearly identify and separate, right? Number one is the disk of the galaxy. So we call that as galactic disk, which is a large and flattened in shape with the built-in spiral patterns of the stars, right? And interstellar matter is there as well. Now, most of the Milky Way's young stars and star-forming regions are in this disk, galactic disk, especially in the spiral arms, right? And so those differences are important when you are going to study about these galaxies, right? And then you have another section called galactic bulge, which is a very small spherical in shape region that lies at the center of the Milky Way, right? And this is a dense region which contains a lot of different types of stars and interstellar matter, and you will see it in the next picture. And then there is a third one, which is called galactic halo. It is a very large spherical shape region, and this halo made up of very old stars usually and clusters, and it normally contains very little amount of interstellar matter. Now let's look at how it looks like in the picture, right? This is a graphic that shows these three structure of the Milky Way. The central region that you have in this blue color, I think it's already marked here, right? Is what we called as the bulge. So that is where you have different types of all the types of stars and a very dense region close to the center. This is the galactic center. And you have the disk of the galaxy. This is the disk, this purple one. And this is where you have a lot of all the spiral arms and also active star forming region. So new or young stars are always in that region, right? And then you have this large halo. So this is called the halo. Halo is where you have a lot of older stars that I have explained here. Very large spherical shape and a lot of older stars and clusters. And it doesn't have much interstellar matter. And halo is the place that where you have a lot of dark matter as well, which we will be talking in a minute, right? Right, now let's look at, so those are the three main parts of the Milky Way. And then let's look at what we have at the center of the Milky Way. Anybody have any questions up to here? Right, so it seems that you do not have any questions. So let me continue with this one for the next probably 10 to 15 minutes, and then we will stop, right? So otherwise it will be too much for one day. And so if you look at the very central region of the Milky Way, you have this bulge, and at the central region of the bulb, you have something called the nucleus of the galaxy. And this nucleus region has a very high density of stars, large number of stars packed in a very small volume in there. And this region actually looks very unusual at different wavelengths if you look at that. And of course, this central region of a galaxy is very difficult to see in optical light. So that's because that region has, heavily obscured by the dust, right? And because of that, you can use infrared, which is less affected or less susceptible to this extinction effects due to dust and gas. And what astronomers have observed is that when you look at the central region of the galaxy, the observation of stars very close to the central region of the nucleus indicated that they are orbiting at very high speeds, right? Unusually high speeds. And also, when you look at the same region from the radio telescopes, it also indicates there is the presence of bright radio source at that particular location. And this radio source is named as Sagittarius A. And what these observations indicate us is that the nucleus of the galaxy, which is the very central region of the galaxy, harbors a supermassive black hole with a mass of 4.5 million solar masses. Right? So this is the finding from these observations. The central region, which is the nucleus of the galaxy, very center of the galaxy, you have a supermassive black hole that has a mass of 4.5 million solar masses. So what that means is this particular galaxy has a mass which is 4.5 million times massive compared to the mass of the sun. So that is why we call this as a supermassive black hole, right? Now the evidence actually coming from this infrared and radio observations. Clearly, when you have stars close to the center and if they are moving at very high speed, there should be an object that is very massive at the center, right? So there is no other way of other reason to have that kind of motion. And if you remember, you have been, I guess, learning about the circular motions. The speed is larger when one orbits. When orbital speed is larger, so that means there should be something very massive at the center, right? Let's go to the next one. This is a schematic representation of our galaxy. So you can see that there are two representations. This type of representation is called the face-on view of the galaxy, right? And this type of representation is called edge-on view of the galaxy. Face-on means if you go up and look how it looks like. So this is like you go look at several locations of the earth from a drone camera, right? So you go up and look at it. So this is something similar to that. So this is called the face-on view, and this is called edge-on view, not the face-on view. So if you rotate this like let's say 90 degrees, then you will see the edge-on view of the same galaxy, right? Right. So now let's look at a little bit in detail about this motion of the stars in the Milky Way, right? If you look at each component separately, especially the halo and the bulge stars, they orbit around the center of the Milky Way. However, their motion is very random. So that means they will move on to different directions. You will see it in the next image as well. So there is no proper arrangement of or proper direction that they are moving, right? So they just move here and there. So especially in the stars in the halo and the bulge. However, if you look at the disk part of the galaxy, the orbits are more ordered, right? So that means they have a certain order and they will revolve or moving around the same direction on the same plane. The only thing is stars that are close to the center move more quickly. So that is basically because of that the supermassive black hole is there at the center. and the sun orbits at a speed of 240 kilometers per second, right? And the sun orbits the Milky Way every 240 million years. Now you can see that the speed of the sun, it's every 1 second we are moving 240 kilometers, right? The sun in the Milky Way. I mean, we don't feel it, but this is what happens. So this is just a schematic picture of what I have explained. You can see that on the disk, so they are nicely ordered and move into one pattern into one direction. But for the bulge and the halo, the stars are moving in every direction, right? So all over the place. I'm going to skip this. And this is an image shows you the near infrared view of the galactic center. And all these circles that you see are actually simulated or tracked circles of the stars that are very close to central region, right? And you can see that all these stars, when they come close to the galactic center, they just move very fast in this particular region. So it's the speed increased enormously, right? And this is why, so if you have higher speeds, when it gets close to the central region of the galaxy, then what that means is close to the central region, there should be an object that can create a very huge gravitational force, right? Now, this is why we used to tell that there is a supermassive black hole and mass can be also calculated, and that's why it's given there. Now, so that is about the central region of the galaxy, but if you take the whole galaxy as Milky Way, the question is how much mass is contained within the Milky Way, right? So one method of estimating the mass is to use the orbit of the sun and use the Kepler's laws. The Kepler law, mass equal radius to the power 3 over period squared. In that way, you can use the sun orbits the galaxy once every 240 million years. So that is the period. And the radius of the orbit is around 26,000 light years. So that's the distance to the sun from the center of the galaxy, right? So that is 26,000. If you convert these two properly and plug those values here, once again, if you remember, I have specifically mentioned when you use these kind of equations in astronomy, you need to make sure that you are using correct units, right? And correct unit is not the standard SI units in astronomy. Keep that in mind as well. Certain equations that you have to use certain units to make it work, right? Because the units are incorporated into the equation itself. And if you plug these values here, you will get the mass of the Milky Way. So approximate estimate is about 10 to the power 11 solar masses. And so this is equal to 100 billion suns. And actually, if you look at the mass even beyond the sun's orbit, because the sun's orbit is at a certain pace, Milky Way extend even beyond that, right? So if you indicate the total mass in that way, then the total mass will be 2 times 10 to the power 11 solar mass, right? Now the question is, that's okay, you have the sun at one of the spiral now, so you can incorporate all the other stuff that is beyond even the sun, so we can calculate the mass. Then you have this value 2 times 10 to the power 11 solar masses, right? Now the question is there anything further out? So that means, is there anything that we have not detected apart from this, this amount of mass? Actually, it seems like while there is very little visible matter further out, so that means if you look at from different telescopes, from the electromagnetic spectrum that we build like X-ray and all kind of telescopes, there is very little visible matter further out and a small amount of gas which enable us to measure the rotation period. So there is small amount of gas further out. So what that means is, I mean, when you go, to these outer regions, if there is very little matter and a small amount of gas is only available, according to our observations from a telescope, then what you will expect is uh, the speeds, the rotational speeds of those gases and materials should decrease when you go further out. So I hope all of you can understand this according to this rotational motion. So the circular motion, uh, the matter is becoming less when you go towards the outward region. Your rotational speeds should decrease. So that is our assumption, or that is what we know from our physics knowledge, right? However, very surprisingly, when you look at the rotational speeds, these rotation speeds are found to increase slightly, right, out to a distance of over even 100,000 light years. So that means there should be some kind of matter that we cannot detect from any kind of telescopes that we have made for various regions in our electromagnetic spectrum. However, the effect of that matter is working, right? So that's why when you expect for the rotational speeds to be decreased according to the available visible matter for us, the rotational speeds have increased. So that means there should be some kind of matter which is invisible, which is we cannot detect from our available telescopes as well. And but however, there is this kind of matter available which gives you the gravitational effect, right? Gravitational attraction effect. And this unseen component of the matter is what we call as the dark matter. Now, I hope you can understand why we call that as the dark matter, right? And here is the curve that we observe, just to make it clear. Now, what astronomers expected is this dashed line, and you can see that clearly. Initially, you get the increase of visible matter. So you will get higher rotational speeds. And after that, when you go outside in the Milky Way, so I have also plot the Milky Way picture here. When you go outside the Milky Way, what we expect is, because you can see only little amount of visible matter and gas there, what you expect is this curve will drop down little bit like that, because there is not enough mass to create higher rotational speeds, right? And however, when they have observed this available visible matter and found this rotational speeds, this is the curve that they got for those matter in blue line. So this indicates that if you get this curve, so that means there should be more matter in this region that we have not seen, right? And we cannot detect for any kind of telescope. However, it is there, and they act as the same way how this visible matter works under gravity, right? And because of that, this kind of matter is called dark matter, because we don't know, right? And this is how the dark matter came into play, right? Right, I guess let me, since we have talked a lot more, there are some slides that are remaining here. So let me stop from here for now, since we have been going continuous for some time now. Are there any questions up to here for anyone? Any type of questions for you? Now, there are actually different measurements that we can take to get an idea about this dark matter and different types of galaxies. Now, one of these measurements is called mass to light ratio. And then we will just talk a little bit about what is this dark matter a little bit furthermore, what kind of things that could be this dark matter. And then we will move on to talk about different types of galaxies and how the galaxies are classified into different types. And it's kind of, just, read through section about the galaxy. So I may do it, or maybe will ask you to read it. I mean, you can, all the notes are now available in the classroom, Google Classroom. You can now go and download it and read it through, because those things are not, logical or something like that. That's information, right? So you can just read through these few slides. I will try to, scan and go through it a little bit, but it will be helpful for you if you can read it, right? And the other message actually that I want to convey to you is that most probably we will not have another lecture for this week. Even in the weekends, I may not be able to take lectures. If possible, I will take 1 or 2 lectures. Other than that, actually, we have another 3.5 lectures remaining, which is basically we will talk about, galaxies and the distribution of galaxies, which is about the expansion of the universe and all this stuff, and then about the Big Bang, right? And there is quite a lot of stuff that we have to talk. And if the time didn't allow, I may get an extra hour separately to finish it. And then I will also give you a second set of problems at the same time, so you can try it. And I have given you the first set of problems as well. In a separate time, I may record, I will give you a recorded lecture for and answers for those tutorials later. And I may have a recorded session for you, or I will do it as a live session like this, like solving problems as well. So that will come actually a little bit closer to your exams, maybe, towards, I mean, I will finish everything, the lectures by the end of next week. However, I will give you some time to try those problems, and maybe I will upload the recorded session for you to go, which I work through, and you can look at it and with the answers to look at those. If time permits, I may get the session like a 1.5 hour and try to explain some of these important concepts. I mean, some of these problems solved in real time as well. So that depends on the time. However, you have, please make sure that you go to the lecture notes and understand and completely understand what I have mentioned in the class, right? And I will upload all the recorded videos as well, like very soon, which are not uploaded until now. Right, seems like you do not have any questions. Then let me stop from here, and we will try to meet at least once in the weekend. If not, the next 3 or 4 lectures, before 3.5 hours to 4 hours lectures, I will take on within the next week, a certain point, right? Right, so thank you for joining, and I'm going to stop sharing and finish the session as you do not have any questions, right? Even please